Welcome back to the channel. In today's video, we will demonstrate how to determine the dimensions and reinforcement of a pad foundation using a worked example. A 350 mm square concrete column supports a dead load of 400 kN and an imposed load of 300 kN, assuming a permissible bearing pressure of 100 kN per square meter. How can we find suitable pad foundation dimensions? The first step is to calculate the total loads, which equals dead load 400 kN plus imposed load 300 kN. This results in a total value of 700 kN. The required area is then calculated by dividing the total load of 700 kN by the permissible bearing pressure of 100 kN per square meter. This gives a value of 7 meters squared. As a result, the width of the pad equals the square root of the area, which equals the square root of 7 meters squared. This gives us a value of 2.65 meters. The overall pad thickness is typically 1/6 of the maximum planned dimension, but not less than 300 millimeters. The pad's depth is equal to 2.65 meters divided by 6. This gives us a value of 0.45 meters. Therefore, we'll use a 2.65 square and 0.45 meters deep pad foundation. We now need to figure out the reinforcement. The foundation is designed as an inverted cantilever that is subjected to an upward load caused by ground pressure. The value of this pressure is the factored column load, which is 1.35 times dead load 400 kN plus 1.5 imposed load 300 kN, giving us total design load of 990 kN, then divided by the plan area of the pad 2.65 squared. This results in a ground pressure of 141 kN per meter squared. If the pad is uniform in thickness, the self-weight can be ignored because it does not cause bending. The critical section for bending is assumed to occur at the face of the column. The required design moment must put the free body into moment equilibrium. Therefore, for a square pad with planned dimensions of length L supporting a square column of width C, the design moment is equal to the ground pressure, multiplied by the length, multiplied by half the length minus half the column width, multiplied by half the length minus half the column width. Half the length minus half the column width equals 1.15 meters. As a result, the design moment is equal to the ground pressure of 141 kN per meter squared, multiplied by the length of the foundation 2.65 meters, multiplied by 1.15 times half of 1.15. This results in a value of 247.1 kN meter. An effective depth, D, is assumed and the tensile reinforcement is then determined as though the foundation was a rectangular beam of width L. We could conservatively use this equation to work out our reinforcement. Design moment equals 0.713 times area of steel, times steel characteristic strength, times the effective depth. There are a few simple rules to follow when it comes to reinforcement spacing. If the bars are too close, they impede the placing and compacting of the concrete, causing voids to form. Minimum spacing of bars equals bar diameter, or maximum size of aggregate, plus 5 mm. Maximum spacing of flexural reinforcement in slabs equals 3 times slab thickness, less than 400 mm. Maximum spacing of shear links equals 0.75 times beam effective depth. The reinforcement is, of course, placed in the tensile face of the foundation, which is the bottom. The foundation will also contain the starter bars for the column reinforcement. Let's get back to where we were. For concrete cover of 50 mm and assuming 16 mm bars, the effective depth of the top layer of reinforcement equals depth of the pad 0.45 times 1000 minus the cover 50 mm, minus bar diameter 16 mm, minus half bar diameter 8 mm. This gives us a value of 376 mm. Now we should be able to find the reinforcement required, which equals design moment 247.1 kilonewtons meter, times 1000, times 1000 to convert it to Newton millimeter. Divided by 0.713, divided by steel characteristic strength 500, divided by effective depth 376 millimeters. This gives us a value of 1845 millimeters squared. The reinforcement should be greater than the minimum reinforcement required 0.15 times foundation length 2.65 meters, times 1000, times effective depth 376 millimeters, divided by 100, which equals 1495 millimeters squared. The number of 16 mm bars equals area of steel 1845 mm, divided by the area of rebar 201, which equals 9.2. Therefore, use 10 number 16 mm diameter high-yield bars in both directions. In the next video, we will carry on using the same example and show you how to work out the punching shear. Thanks for watching. We hope you found some useful tips. Check out our website at structuralengineercalcs.com. Please like and subscribe, and let us know what would you like to see next. The human footprint is a masterpiece of engineering and a work of art. Stay safe. Goodbye, and see you soon.